All right, hi everyone. Welcome to this implementation lecture on transformers. So we're going to take you all through again the same sort of patterns we've had the last few implementation lectures. We're going to implement a native NumPy version of kind of the reference implementation of, in this case, transformers as they're implemented in PyTorch. You will, of course, in the homework, implement these in Needle. Actually, there's no homework for transformers, but if you want to use them in your project, you'll have to implement it in Needle. But we're going to do it in NumPy to kind of show the simplicity of this. And the reality is, in Needle, you will have to implement a few more things, especially as we'll talk about later on batch matrix multiplication. But at least because these things are already implemented in NumPy, you can highlight kind of the simplicity of these things just by looking at a NumPy implementation. All right, so let's go ahead and get started here. Let's start by importing all our libraries. This would be just the PyTorch, NumPy, torch. All right, and so we're also going to refer to some of the sort of basics of our sort of the mathematical equations of attention. But to start off with, we'll just implement kind of these basic operations here. Okay, so to start off with, let's talk about implementing the basic kind of attention mechanism we've talked about, which is essentially what we have to implement is this output y. Output y is equal to the softmax of k q transpose over root d times v. And the way I framed it last lecture is that k and q and v were the inputs to self-attention. But what's a bit more common, and this is, for example, the convention that PyTorch takes in its own module, is that you actually make the self-attention a module in and of itself, and you include the weights that manipulate the input, the weight to get the K matrix, the weight to get the Q matrix, etc., as part of the actual layer. And so what we're actually going to do is something more like the following. We're going to implement a layer that has WK, WQ, WV as parameters, and we'll actually implement something like softmax of K X times WK, Q transpose, which would be WQ transpose X all over root D times V. And it turns out, actually, the convention for most frameworks out there is to add another linear projection after this fact that actually also have some additional W out term. This is, of course, oops, I wrote just V there. It really should be X times WV. This, strictly speaking, is not really necessary, right? Because you could always just lump together W out into WV there. But especially when it comes to multi-head attention, we'll see why we might want to do these things separately. So we'll actually have a separate matrix here to follow kind of conventions. All right, but this is the basic operation we're going to implement here as a self-attention layer. And the parameters of this layer will be WK, WQ, WV, and W out, which will actually be implemented as a linear layer. Now, in some cases, some of these terms have associated bias terms as well as the weights. We're going to ignore the biases and set them to be 0 so that we won't worry about biases. If you want to include biases, it's still already quite simple. Okay, so let's go ahead and start implementing this thing here. All right, so to start off with, we're going to just implement basically the function you saw before. There's no built-in softmax, and in NumPy, of course, you already have this in Needle, so you wouldn't have to implement this. But let's just build a simple NumPy softmax layer. That would be something like take the exponential of z. Actually, yeah, I think this is z minus z max over the last dimension. We'll always take the softmax over the last dimension. equals true to make it keep safe dimensions there, and then we will set z to be equal to z. We'll just normalize z dot sum axis equals -1 and keep z equals true. Okay, so that's or sorry, we'll return that, and that's our softmax function. Okay, now we have our self-attention. And remember, self-attention is just literally nothing but this that we saw here. So the way we implement that is we implement softmax or self-attention, and we're going to take one input x, right, and then create all those three terms. We're going to take a mask too that we might adjust it by, and then we'll take the weights. And if you look at this equation here, if you look at this equation that we saw on the previous page, what we're actually doing in some sense is we're forming three things, right? We're forming k equals x times wk, q equals x times wq, and v equals x times wv, right? But because we always want to sort of have the largest possible matrices multiplied together as we can, it doesn't really make sense to do a multiply, to do three multiplies kind of separately for these things. What we should actually do is form kind of a matrix that contains all of k, q, and v together, and form that as just x times a matrix that sort of contains wk. Move this over a bit. That contains wk, wq, and wv. Right, and we can do that kind of all in one go here. Of course, this could also just be written as x times w, like kqv, like one matrix that sort of contains the concatenation of all these things. And in fact, this is really what libraries like PyTorch do internally. So internally, just like with LSTMs, they didn't really store a separate, each separate portion of the different hidden and input gate, output gate to hidden, and they just have sort of one matrix, right? They did that here with self-attention too. So sort of one matrix sort of contains your weights for the K, Q, and V matrices all together. All right, so let's see what this looks like now in terms of implementation. So we would pass also W, K, Q, V, and W out. All right, and the first thing we'll do is we will form K, Q, and V. So we'll form K, Q, and V equals here. Well, it would be x times W, K, Q, V, but we have to then split it so that it's sort of consistent, right? We want it to be the same. Each of these to be the right size here, right? So what we actually call is split WKQV. Again, we'll split it into three components, so the K, Q, and the V, and we'll split it over the second axis there. So it's over axis equals 1, right? Again, X here would be a T by D dimensional matrix. The sizes from them are all, the other ones are all the same, but this is sort of the second dimension we split over according to what we saw previously on the little notebook. Then we'll define our attentional weights, which is going to be the softmax. Again, this is applying softmax kind of row-wise, so it's the correct term there of K times Q transpose divided by square root of D, which is shape 1. And then we'll add to this our mask. And the convention is to actually add masks rather than subtract them. I know we wrote subtracting them, but we typically add negative infinity instead of subtracting infinity. All right, and I think that's it. I believe that's all that there is to it. Then we just have to return the the one thing left to do then is that's our attention matrix. Then we have to return, of course, our attention matrix times V. That's the main thing that we want. And then for good measure, though we'll see why we do this in a second, we also multiply it by W out. And we can also return our attention matrix if we want to. I think it's rather common to return both the actual output of the attention layer plus the attention matrix itself. All right, so this is our attention. Oops, I think I didn't run the cell. This is our attention matrix, and then our attentional self-attention call. And now we can compare it to PyTorch. So we can look to see what is the actual, how does PyTorch really stack up against this? So let's say t and d equals a time of 100 and then hidden dimension of 64, say. Let's form our sort of real attention, or I guess the PyTorch attention. And we'll use the multi-head attention call there. And the arguments of this call are, first, you have the embedding dimension. Let me just create some more space here. First, you'll have the embedding dimension. Then you have the number of heads. We'll get the heads in a second. And you have some other terms as well. So you have whether there's a bias term, we'll make that false because we don't want a bias term, and a bunch of other terms that we aren't gonna worry too much about there because they're actually not used that frequently. The one that we will use, I should mention, is this batch first dimension. But we'll talk about that when we get to batching. Okay, so we're going to have D be our hidden dimension, the embedding dimension. One head for now. We'll talk about heads in a second. Bias equals false, and batch first equals true. This is going to make the batch dimension the first dimension of the input. We'll talk about that more with batching. Let's create our mask. So let's make the mask equals a upper triangular matrix of infinities. So on the upper triangular matrix, there's going to be negative infinities. And then torch.ones, a t by t matrix of infinities there, and we'll do it one off the diagonal. So that looks something like this. So the lower triangular portion is all zeros, and the strictly upper triangular portion is all negative infinities. And then we will set our input sequence to be torch.randen, just one. Again, we're just testing random inputs here to see if these things work or not. Batch size of 1 for now. We'll deal with batches in a moment. And let's get our true kind of output here. Is the attention time of applied to, and the convention of PyTorch is that you actually input you form the input 3 times to get the 3 different components of it, but we're just going to multiply it by one. Ours just has a single call, of course, right? We don't put it in 3 times. And then the attention mask equals m. All right, so that gives us our ground truth output. There's no real point in inspecting it. It's just random. It's just going to be random numbers, but what we actually want to do is compare to sort of our version of this. So let's also then compute our outputs. So y and a equals our self-attention, x0 numpy, m.numpy. And now we need to have the actual weights and everything. So let's look a little bit at the model. So let's look at our attention model and see what weights it has. So the first thing you'll note is this in projection weight and in projection bias are this actually is exactly this. That's exactly this WKQV here. It would be a bias term that it would have as well. And so we're going to start with that as our as the thing we multiply by. But to get KQV there, and that really is KQV, and if you just look at the shape of it, so it's 3 times 64, but really, so our version of that would just be that thing transposed. So we just take as input tension.inProject weight. We want to attach it, numpy, and we want to transpose it because in our convention we post multiply by it, and that would need a 64 by 192 dimensional matrix. And then we need to also multiply by the out projection weight, which is this term here. So that's this term. And there, for that purpose, PyTorch has a separate linear layer in this, which is called out projection. So that's, well, let me just go up here. Out projection. So this is a it's basically a linear layer, despite the funny name, sort of a special linear layer, depending on how you can quantize it, I guess. But this is basically a torched out linear layer. And then it has a weight associated with it, and it has a bias. And so we can see what size it is. It's 64, as we'd expect. And so the weight and detach numpy transpose. right? And that should be everything. Okay, then we can compare norm of, we can look at the difference between A minus the true. Of course, the true one would be different for each batch, so we need to do this, numpy, and look at that. And as expected, both this and our outputs are the same. So we're doing the same things that PyTorch is doing here, again, with just sort of this call here. Okay, so that's sort of the thing that PyTorch is doing internally with this sort of, at least with multi-head attention when you call it with a single head. That we'll talk about heads again in a second. All right, so let's now, the next thing we'll talk about, so that's sort of our basic implementation. But of course, this is not, this is sort of one layer of self-attention that works for a mini batch of size 1 that doesn't have, that has what's called a single head, which is not what we'll use in practice. In practice, we'll use something called multi-head attention, which we'll talk about in a second. But before we do that, let me talk about the next element of order here, which is mini batching. Let's talk about mini batching. Okay, so when we want to do mini batches in attention, let's look at the let's look back at the formula for what we had for self-attention here, and I'm just going to look at this sort of equation here. And if we have, this is sort of for a single batch, right? So for a single batch example, K would be a T by D matrix, right? For a single mini batch. And if we have many batches, then, we'd want to somehow contain more than one batch in a tensor. And remember, we have some sort of, some options here, right? So what we did in RNNs is we had a T by sequence, T by batch size by D dimensional tensor, because we wanted to sort of batch multiply these matrices together, B by D matrices, because we had to process each time series in sequence. So we'd use this, basically for RNNs. Right? For transformers, though, we're doing this sort of multiplication in batches, right? We're forming K times Q, which is the last dimensions of, which is the T by D dimensional matrix. So what we're actually going to do here is we're going to use a kind of adopt more, or rather what we should do to keep our multiplications contiguous in memory, is adopt kind of a more standard approach and actually use batch by T by D. Now, PyTorch, if you defaults actually to this format for self-attention. And that really makes no sense kind of computationally. It's only done that way such that so that you can swap in and out transformers for RNNs kind of one-to-one and not have to worry about reordering your batches. But really, we should be implementing a transformer like this. Take the batch dimension first, and then do matrix, then do multiplications over the two trailing dimensions, which is going to be more efficient, of course, because these are going to be contiguous in memory. So what we should be doing is this one for transformers. Again, PyTorch does not do this. This is why we have to pass this batch first operation that you saw earlier. This, what was that here? Batch first equals true. That means the first dimension is the batch dimension, not anything else. Okay, that's sort of the first thing to know about batching, is that we're going to implement our batches like this, not like we did with RNNs to sort of do that. But let's think now a little bit more about sort of what we want to do to process these in batches. What we kind of want to do is we sort of want to form, like, we have our different, our different batches, like K1 or K2, right? So if we have, softmax of our first, that's not like the first row of K, that's like our first whole big K matrix, and Q1 transpose, this forms, the output of our first batch. The next one would be the output of our next batch, etc. This with this with Q2 there, K2 would be our next batches, etc. Okay. But it turns out there's actually a subtlety here that is worth mentioning. Because in order to do this, just think about just forming, all multiplications of ki times qi for every element in our batch. It turns out to do this, we actually need a new call, which is called a batch matrix multiplication. Also sometimes called a BMM call. And it's subtle why we need this, because after all, we've been doing batching for a while, right? Like in convolutional networks, we had batching. So why do we need some sort of new kind of call for batching? It turns out, though, that all the matrices we've done previously, we all could have done that multiplication, or all the batching we had there, we could sort of do still with a single matrix multiplication call. And sort of what I mean by that is, previously, even when we had like, you remember, like to do a, for example, to do a convolutional call, right? We would do something like y equals m to call of x. So y1 there, right? Equals. I probably should have actually used. Let me use superscripts here to talk about batches. That's probably what I should have done, because I use the other ones for time. So let me do that for batches. So previously, if we have, the batch 1, we would call m to call of x1 and then multiply it by w. But of course, and this would be a matrix. And we would do that for x1 and x2 and x3. So let's do, this is a matrix here, this term's a matrix, and this term's a matrix here. But it turns out if we want to get kind of all the different y's, we don't actually need to do anything but multiplication. We could just sort of say that y2, all of them together, kind of, y1, y2, etc., is going to be equal to m to call x1, m to call x2, etc., all times the same term w. Okay? And so whatever batching we had before was actually just attainable by taking, whatever tensor we had in our first multiplication here and just kind of, flattening it out to a matrix of the proper size and then recompressing it to be the right size. So you didn't actually need, and you probably have seen this if you've implemented homework 4 when you did convolutions, you'll see that we didn't need anything more than this. We could just do everything we had with this, your ordinary sort of matrix multiplication call that you had in Needle. For transformers, though, we actually need something different. We need a batch matrix multiply call, which says for all the k and q's, form this inner product. And to sort of highlight this difference, I want to go actually to talk about this sort of illustrate this in NumPy here. And just with some random matrices here, right? So let's take like c equals and then 5 times 4 times 10 times 3 or something like this, right? And let's make d equals, and I didn't want to use a because I think I use a elsewhere, so I'm just starting with c. Let's just do it like 3 times 6, right? So if I multiply in NumPy these things together, then my output basically is the leading dimension. So for every input in the leading dimensions here, I take the corresponding 10 by 3 matrix, multiply it by this matrix, okay? But to be very clear, this isn't really batch matrix multiplication, because this thing here is the same as if I just say, view this basically as a whatever by 3-dimensional matrix. So let's look at the shape of this. This would be a, oops, I'll just reshape it like this. 200 by 3-dimensional matrix. And I think this shouldn't do any, this shouldn't copy memory at all. If I just did that, multiplied it now, this thing by D, this would be a 200 by 6-dimensional matrix, and I could then reshape this thing into a 5 by 4 by 10 by 6 matrix, And that would actually be the same thing as just multiplying C times D. So this will be all zeros. Okay. So this is maybe saying a lot here just to make a really simple point. There's nothing batch about this matrix multiplication here, right? This is just matrix multiplication. This is a matrix, and this is a matrix. They're both just 2D tensors. And so this thing here, even though this is a higher order tensor, the actual multiplication can be accomplished with normal matrix products, right? So a 2D tensor times a 2D tensor. All right. That is not the same for something like this. All right, so what this is doing, oops, that's the same dimensions. What this here is doing is it's taking every corresponding entry and computing the product of the trailing 2 dimensions. So this is going to be 5 by 6 by 4, but you can't have different sizes here. So you can't have like this is 5, 4. This won't work. To do for higher order tensors to be multiplied together, either the second one has to just be a matrix, in which case it flattens the first one, or the second one has to be the same. The leading dimensions of the second one have to be the same as the third one. So and then you just do sort of multiply the corresponding things. So it's important to note this seems like I'm glossing over here, but essentially it's important to note that something kind of deep is going on here, which is that this operator in NumPy is doing something actually quite different when you. So here it's sort of doing like a loop, a for loop over all batches here, whereas if you do this, it's just doing a single large matrix product and then reshaping things accordingly. All right, so those are 2 very different operations actually. What we want for self-attention is a mini batch, is a batch matrix version of this. But the good news is that it actually is a very small set of changes that we need to make to our matrix here, or to our sort of function here, in order to make a batch version. The only thing we have to change actually is because we're all doing sort of batches there, if we just make X be a batch by T by D tensor, everything works here. We just have to sort of use a few different tricks. So let me just talk about what those tricks are. Let's define one that works as batching. I'll just call it the same thing because there's no point in defining a different term for this. But basically all we have to do is just, we're going to be splitting on the second dimension now in theory, but you know what, let's actually make one that will work in both cases. Let's make it one that'll work in both the batch case and the non-batch case. We might as well. So that's gonna, this is going to take the last axis and split it on the last axis, which will be either, the third or the second. Also make D be the last shape, not this. And then transpose doesn't transpose always the last 2 dimensions, but it will just transpose some dimension. That doesn't really work for higher order tensors. So we have to actually say swap axis. We use the swap axis call here, and we'll swap the last 2 dimensions there. But other than that, that is now a self-attention call that will work in batch form, exactly the same as before, just with, and it'll also work in non-batch form. So it in fact works for both these cases. So let's go ahead and test that one actually. Let's test this with the only difference being that, let's say that B here is going to be equal to this. And let's also set B to be, I don't know, batch size of 50. And then let's make X equal torch then of B by T by D. And then the mask is the same thing as before. The mask doesn't change. The mask is applied the same mask to all these things, so it should just work. Oh, I might need to actually do one thing. No, this will work because I think that the dimensions will work properly for the batch. You don't need to, because it's the trailing dimensions that need to sort of be broadcast. That just kind of works. Make the mask the same thing just for the sake of it here. We'll add that there, and this is out now. So let's test out y a, the true y and the true a is going to be attention x, attention mask equals m. Let's see if I got the sizes right. Okay, I think I did there. And then let's look at ours. So let's add our ya equals self attention x mask wkqv and w out. Okay, did run here or something. This there. Oops, m. Oops, I didn't. That's right, that won't work. I meant just copy my call from above. So let me do that. This is what I wanted to call. The only difference is I don't want this first one there. I just want that, and that should work. Okay, and now let's look at norm of y minus y attach numpy. All right, it's looking good. It's the same thing. So now we have a batch version of matrix multiplication of self-attention working. All right, so we're actually kind of almost getting there. We have almost listed up all the ingredients we need to build our transformer. The only missing ingredient is multi-head attention. So attention, as we described it before, is actually not usually applied in this way. So the problem with self-attention, as it was, as we sort of described it before, is that when you're forming this, let me go back to the board here. When you're forming, say, this KQ transpose matrix, this is a matrix, so this equals some matrix here. And as I mentioned before, sort of the I, J entries of this matrix is equal to Ki transpose times Qj, where Ki is the ith row of K and Qj is the qth row of Q. And if these are each, if Ki here is d-dimensional, so basically if K, remember, is T by D, that means Ki, the ith row of K, is d-dimensional. And you're using a d-dimensional inner product to ultimately compute one number, which is used to weight these things together. And while this is a bit of a hand-wavy argument, what I would describe, the way I would sort of put this is, that is not, the nonlinearity of the attention layer. I guess there's also multiplication of things together, but sort of the key nonlinearity is like the softmax, right? You're getting different averages to add up together to sort of make your you're getting an average of the different rows of Q to all give a weighted sum together to produce your output. And somehow doing that only once for all this work to form big matrix multiplications seems like kind of a waste. It sort of at a high level, kind of the intuition here is you want to cram kind of more and more nonlinearities, as many as you can in some sense, into your nonlinear operator like this to sort of get the power of nonlinearities for deep networks for function approximation. And just doing this once with these really big inner products here is kind of a bad use of nonlinearities. To kind of, again, give a little bit hand-wavy, but I think kind of intuitively correct argument here. And so what the common thing to do is instead of producing just one application of attention, we're actually going to produce many of these, H of these, where H is a parameter known as our heads. So we're going to have what's called multi-head attention. Multi-head attention. And what that does is that takes our K, but also our Q and our V, and partitions it. So K is going to be now equal to K1, K2, etc., up to K times the number of heads we have. I'll just call that little h, KH. And Q would be the same. So Q would also equal Q1, Q2, blah, blah, QH. And importantly, I'm doing this by splitting the columns here, right? So the rows of these matrices are the individual time points. I'm taking each sort of slice of time, a row in time, and I'm chopping it up into H different components. So this is an H here. H. right? Then what I do is I form a number of outputs, like my yi would be the softmax of ki qi transpose. Not, again, these are not batches. This is for a single example. So we're going to do the same thing, you know, eventually the same thing by batch, but that will require a little bit more, little bit of care to do both multi-head and batch attention, but we'll get to that in a moment. This is now just doing it by the different heads for a single example. Divided by d, but it's now d actually going to be the square root of d divided by h, because we want it's each I here, you know, each row here of this matrix, so each sort of subgroup of this matrix is going to be t by d over h, right? So you have this of the h times vi. And then our final y, the final output of the sort of softmax layer, is just going to be all those y's together, y1, y2, etc., to y h, and then I guess you also multiply by this w out, which again could just be folded into all the other matrices, but let's not worry about that. That can be done after the fact if you want to. Okay, so that there is our multi-head attention. Let's go ahead and implement this, and we will need a bit of care here when we talk about doing this in a manner that allows us to do sort of these multiplications kind of in the proper way, while also preserving the batches properly. All right, so I'll talk about what I mean by that, but then we'll sort of see. Yeah, we'll sort of see what I mean by that. Okay, so let's talk about how we go at implementing this thing. So let's define another operator, which we'll call there we go, multi-head attention. We'll take also x, the mask, but also have a parameter which is the number of heads. We'll take again w kqv. Nothing changes with that of the sizes of these things. We just are applying self-attention to blocks there. Let's just for the sake of it also get b, t, and d is the shape of x, because it's a little easier just to use those numbers instead of getting the shapes of x automatically. Now let's sort of form our self-attention. So first we'll do the same thing we did before, which is to say we take x times w kqv, and we split it into 3 components along the last axis. All right. Now we're going to do a little bit of a tricky thing. Right now, k, q, and v are, as I said, they are k, q, and v are, what size would they be? Well, they'd be b by, I gotta comment on this. These are like, k would be b by t by d dimensional matrices as well, just like x. But what we want to do is we want to split this into a different size, right? We want it to be instead b by t. Well, what do we want it to be? We want to still multiply at some point a batch by t by d divided by heads size. And we have to be able to multiply sort of these matrices together, right? Because we still need a t by t matrix for each of those. So we really want to somehow convert this to a b by heads by t by d divided by heads. Okay, so we could do this by saying, like, you know, k dot reshape. And well, first of all, we have to reshape it to be b by t by heads by d divided by heads. But then we need to swap kind of this term, this axis and this axis there. So we're going to swap the axes of 1 and 2. By the way, if I think we're starting to the point where, like, doing this all would be way nicer with named axes or named dimensions here, which is one feature that PyTorch has that I admit I don't use, even though I probably should. But it might be nicer if you sort of keep track of these. But what we're doing here, this would convert this to a to this format, right? Because we convert to the heads by t by heads, and we swap these two, so then we get heads by t. Okay, so that would convert k to be a tensor of the form that we want for batch matrix multiplication. I'll just cheat a little bit here and do like one kind of like this. I don't want to repeat this I don't want to repeat 3 lines of this, so I'll just do them all at the same time. Let's just do for A and KQV. KQV. So this just does the same thing for all of those, right? This will do it in one line. Okay. Now we form our attention matrix. So let's say our attention is going to be equal to the softmax. So again, works fine in the batch setting because it's applied to the last dimension of everything here is the same because k times q, swap axes, -1, -2, that's all the same. These are now 4 order tensors, but we're forming like this. We're just transposing these 2 elements here to form our attentional matrix. We're dividing by the square root of d, number of heads, and we're going to add the mask. Okay, so now we're good. All we have to do last is sort of multiply our tension by v. But now we have something kind of the wrong size, right? Because now we have a matrix that is this size, and we want to convert it back to this size. So what we're going to do is we're going to sort of swap axes to 1 and 2 again. That swaps the heads and the t-dimensional axes there. So it's going to be back to t by heads. And then we're going to reshape this to be batch by t by d. Okay, then finally multiply by w out and return this and the attention. And I think that should be it. All right, so let's do everything again. Let's just set heads equals 4. Let's create attention is a now and then multi-head attention, multi-head attention. D heads 4, bias equals false, and batch first equals true. Get our true outputs, attention x, and then attention mask equals m. All right, so this is our ground truth. And now we have y and a equals our multi-head attention, x.numpy, m.numpy, heads, and I'm just going to copy what we did before. These all stay the same, so nothing changes here. All right. And oops, what did I do wrong? Oops, I called that shape. I meant reshape. Okay, and let's compare y. Sort of save one around to give me space. Norm of y minus y attach.numpy. Okay, and it looks good. Now, one thing to keep in mind is actually what PyTorch even returns here. So let's try this for A. Actually, I think something will go wrong here. I'm pretty sure. Yep, something's. And so what's oddly happening here is that you know, our attention matrix is sort of rightly. Well, we have 50 batches, right? We have 4 heads. And then each head has an attention matrix, so it's 100 by 100. So this is the right size of the attentional matrix. But if you look at the output of this, it's only 50. And I believe what PyTorch does is it returns the average attention over all the heads. I don't know why this means anything or why this should mean anything to anyone, but this is what it does, I believe. So if you look at this, if you look at the mean over the axis equals 1, I think this will tell you it's the same thing. Yeah, so you know, ours is, again, ours rightly returns all the attention matrices for each head, but PyTorch just returns them for each one. Okay, so now this is our multi-head attention. Again, not you know, five lines of code. Now now we're ready to put it all together and create a transformer block. All right, so what is a transformer? Again, a transformer is just a, I don't know if I want to write the whole thing again. It's honestly faster to write it in code than it is to write it as the equations. But I suppose I'll sort of write at least the high level. I'll like draw the diagram here. So what a transformer does is it takes X as input, forms from this K, Q, and V. Q and V, puts these three into self-attention, adds together the input as a residual layer and puts this into layer norm. Ran out of space there. Layer norm. Then puts this into a feed forward network, which is just like a 2-layer network. So it's gonna be a ReLU followed by, or linear layer followed by a ReLU followed by a linear layer. Let's call that a feed forward. And then for good measure has another residual connection into layer norm again. Layer norm. All right, so that's our transformer. Honestly, it's actually easier to write this out with code than anything else. So let's write this out in code. All right, so we actually will have to implement like the basic operations here, but we have to first implement like a layer norm call. So let's implement our layer norm. I know we've already done this in Needle, but we have to do it again here. Let's do layer norm. So it's going to be return z minus z dot mean against the last axis, -1. Keep dims equals true, so it properly broadcasts. And then we want to divide by np dot square root of mean of the cursor go. There we go. The variance of on the last axis, -1, keep equals true, and then before taking the square root, we add epsilon, so we don't get sort of division by 0 error. Right? We also need to find a ReLU, so that's just going to be return maximum of z and 0. Okay, and then we finally have our transformer layer. So let's define our transformer. And now we actually have to, honestly, like just having all the inputs to this takes as much time as anything else. Take X, the mask, heads, so we'll use a multi-head attention for our transformer, WKQV, W out, W feed forward 1. There's no option in I believe in PyTorch's transformer to zero out the biases for the feed forward layer, so we'll have to do that manually. But it's easy to include biases if we want to. Let's just not do it because it's kind of a pain. The 2 feed forward layers and epsilon for layer norm. Okay, I spelled transformer wrong. Transformer. All right, so let's first set z equals to layer norm of z or x plus multi-head attention of multi-head attention applied to x, the mask, w, kqv, w out, and and heads. Okay, and then we need to also give it epsilon for our layer norm. Now let's return then. Well, let's now take this output and kind of, feed it into a 2-layer network and apply layer norm there. So let's just return the layer norm of z here plus, well, the ReLU of z times w feed forward 1 times w feed forward 2 and epsilon. Okay, that should be it. So now let's define this. Now let's define like the PyTorch reference solution. So let's define transformer. equals to neural and then transformer. And one thing you'll sort of notice here is that you, when you have these things, you'll notice that there's these like transformer decoders, transformer encoder layer, transformer decoder layer. The thing you want is transformer encoder layer. When transformers were originally formulated in their original paper, they had kind of two different layers that had different size inputs here. Basically, they would share like K and Q terms from the... They basically had an encoder-decoder architecture because they were using it for a seek-to-seek problem that involved translation. So just like with RNNs, you can have kind of two RNNs stacked together, one that encodes it, one that decodes it. They did that with a transformer, but it made actually notation very complicated. So a lot of later applications of transformers, they don't use this sort of things. And in fact, it's a rather like language models don't either, right? Like just this one application of transformers is actually rather complex compared to other ones. But basically decoder depends on sort of the relative sizes of the inputs to them, and will also sort of imply masks or no masks. This is how we'll do it here. But just note that this is the layer you want. If you don't know which transformer you want, you probably want this one, the transformer encoder layer. And so I forget what the arguments are. So this D, and then heads, and then the dimension, and then let me see. So, right, the dimension of the feed forward. Let me pop this up a little bit. Oops, why isn't it doing that? There we go. Dimension of the feed forward is the other argument here, which is sort of the dimension that we see in the in the feed forward layer, because it's two layers. This is the dimension of the hidden layer in the feed forward network, which is typically higher than D. So you sort of like inflate the hidden dimension size and then to get expressive power. There's also a lot of various dropout mechanisms for transformers that are built into these things, but let's not worry about that. Let's just set dropout to 0, and then batch first has to be true to make sort of the batches work also. Okay, so I think we want this. We want dim feed forward. Let's make this 128, say, dropout equals 0.0, and batch first. Oops, I'm losing my... Let's do this here. Dropout and batch first equals true. I think that's my whole transformer that I want. And because I can't actually set my transformer to have no bias in the feed forward layer, just to keep things simple, I didn't add a bias up here, right? This was without biases. I could add a bias, but just one more parameter to the input. I'm trying to show the relative simplicity of this. I can just say, so I think it's trans.linear1.bias. Let's zero that out. Data.0. And similarly, all right. Okay. So now I can set my output to be the transformer applied to X with the mask of M. All right, and that's the true output that I want for this thing here. Now let's try. Oh, actually, sorry. Let me set this to be Y underscore. Okay, now let's set mine. So let's set transformer of x.numpy, m.numpy, heads. Okay, so now we have to pass all the weights. So this is going to be kind of a pain, but let's just do them all. So trans dot, I think it's self-attention. Is it self-attention layer? And then we want the in projection weight. Oh, I also want to set bias. Let's see. I want bias equals. Did it not set bias equals false for the? I forget if it did this for the transformer. I thought it was one of the arguments. Let's see that again. So no, but it must be 0. Like I'll look, but I think for some reason this worked even when I didn't specify bias to be 0. If need be, I can do that. I think the bias terms initialize to 0 by default there, or they are set to 0 initially. So maybe you have to fix it for when you train, but this should roughly work. If not, we'll debug this. then detach. All right, so that's our first. So that's the WKQV. Then we need to say W out. So that's W self-tension dot out projection dot weight dot detach dot numpy. Now we need to pass next the feed forward weights there. So WF1, WF2. So that's btrans dot linear 1 dot weight dot detach. I should have like a little macro for dot detach dot numpy, but well, attach numpy. And finally, let's look at my normalization, the epsilon. Okay, let's see, did that run everything? No. Error there, so. Uh-oh. So what did I do wrong here? So, oh, this should be -1 error norm. I think that's what it was. So the dimensions are still messing up here. Oh, right. This thing that I add as an output would be just the 0th. That is a problem. That's not the problem that's actually causing this. That would be a problem. Definitely would not work, but that shouldn't be the only thing. Let me go back and see what's happening here. That was working fine. Did I pass the wrong weights in? Oh, right, transpose them. All my weights. Okay, still causing some issues. X plus. So let's see again. Okay, so what's this? Shape is that, so that should be the same shape as this. If I pass multi-attention, X masks 0. They should be the same size. So where's that happening? It's happening there. Let me just print this out. I think I just hadn't saved something or something like that too. So that's working. Oh, I think I hadn't run it when I did the 2 or something. I don't know. Okay. All right. So crisis averted. Well, let's see. Y minus Y as our .detach .numpy. All right, and little, you know, the errors are building up a little bit because these are floating point numbers, and we're doing a lot of things to them now. But that's still with a numerical precision for the size this is we're talking about here. Again, this is remember this is a fairly large matrix, so this is a 50 by 100 by 64, and our total floating, the norm of our total floating point error is within machine precision. Okay, so that's going to be our implementation now of a transformer. And again, the point that I kind of want to highlight and really emphasize here is that, this whole thing is 9 lines of code and, 5 or 8 more, right? So it's all less than 20 lines of code. And yes, there's, of course, elements. It's pretty dense code, all this kind of stuff, whether you really want to write it like this in Needle. Yeah, you probably want to split it to a few more lines than that. But these are very simple operations, right? There is a lot of sort of... they're written very verbosely in a lot of the libraries that are out there. If you look through the PyTorch implementation, it'll be a lot longer than this, certainly. And it does, handle more things, right? Just if you look at, if you just look at the definition of this, right? There are a lot of options here that you can kind of go through and add and all this kind of stuff. But and you have to put dropout somewhere, and you have to put sort of, you know, where the norm goes and this kind of stuff. But the reality is, at its core, transformers are very simple operations. You can implement them in 20 lines of code, and if you implement this all in Needle, you would have to implement the batch image multiply in Needle, of course, and that would take some work in the op call and getting the gradients and everything like that correct. But once you actually have all your ops done and just want to write the module, writing a module is just not that, for a transformer, is not that hard. And because it's just based upon matrix multiplication, this will be relatively efficient to do on GPUs. In fact, arguably one of the motivations for transformers is they're very efficient to run because they rely just on large matrix multiplications. All right, so that's our sort of lecture for today. Next time we will have kind of a bit of a, and actually finishes up kind of our dealing with the implementation of kind of the core modules and units of work when it comes, or sort of common modern deep networks. And next lecture we'll talk on some sort of additional topics. I'll talk about implicit models next lecture, and TQ will talk about some additional kind of large scale training and things like this in the following lectures. All right, so hope you enjoyed this implementation, and see everyone next time.